Okay. I'll be referring to the syllabus, particularly when I look at the topics that will be covered on the exam. This is kind of unexpected that I mean, they picked a good week to be shutting down the building. So what I want to do today, this is actually in the matrix algebra section. If you go into or you can actually download it here, or you can go into RStudio on the server. We were a little bit worried about our servers. We actually have universal power supply, but we're not sure how long we weren't sure how long that was going to hold. Are you getting? Oh, good. I was getting a little concerned. What I'm interested in, I added just a little bit to these notes that are not in the notes that you're downloading, but I'll show you what it is. It's just a very few things. Last time we were talking about matrix algebra, and I believe the last thing we actually talked about was special types of matrices. And so you should review this. And again, I fairly quickly talked about some special matrices like diagonal matrix, upper and lower triangular, symmetric. Symmetric is quite important in that it means that the transpose of the matrix is actually the matrix that you start with. And from a statistical point of view, all of these properties, positive definiteness, positive semi-definiteness, orthonormal, and idempotency are all very important. It would seem strange that idempotent says if you square a matrix, it's equal to itself. And that turns out to be a very important property in linear models, as you know, as is symmetry. And positive definiteness is again a property that we use all the time in linear models. Orthonormal, we talked about orthogonal contrast, and that's a similar idea. In this case, we're saying that the transpose is the inverse. And obviously, if the transpose is the inverse, then it's very simple to find the inverse. What I wanted to do today was to look at an example, this air pole data, and sort of go through how you might do it from the analysis of variance point of view. Yeah. So let me take a look at that. There's a data set. You will need this text file. And if you run, this is a text file with the air pole data. And if you run it and we look at the first 6 observations, this is the full data set. And I was wrong last time I was saying that we're trying to predict SO2. That's not. We're trying to predict mortality in cities. And we're looking at things like rainfall, education level, population density, non-white population, NOx, and SO2. The NOx and SO2 are pollutants, of course. And one of the things you might want to determine is whether those pollutants, if you have high concentrations of some of the nitrous oxides or the sulfur dioxide in the air, does that affect mortality? So there are quite a few cities that we have measurements on. And I'm going to look at a subset of the predictors just for simplicity. So suppose we form our X matrix, and the X matrix is going to consist of columns. It's going to consist of a vector of 1s, and that will be for the intercept when we do our model. And then we're going to look at rainfall, education, non-white, and SO2. We're going to look at those 4. And these are all predictors. So I formed a matrix called X. And we're going to try, based upon those 4 variables plus the intercept, we will try to predict mortality. So we need a Y variable, and I'm going to say air pole is column 7. So if I look back here, this is column 7, and so that will give us the Y variable. So I'm saying Y is air pole, comma 7. And if I print that out, this is Steve. Let me take it. Hey, Steve. Yeah. Yeah, I'm sure it did. Is there someone? Yeah. Yeah. Okay. Yeah. Okay, we can try it, but it's just the front 2 rows, not the back 2. So you sure it's not a switch that's been thrown? Yeah, I suspect it's the breaker. Do you know who to call? Since I'm teaching. Well, since I'm teaching, can you do that? Okay. I'll try that, but I doubt. Yeah, I'm teaching now. Yeah. Okay. Okay. You said to try it. Unplugging, holding down the power for 10 seconds, plug it back in, but I don't think it's going to work. Sometimes it will work. You unplug this in the back. And plug it back in. And I think it's a breaker. Yeah, it's not working. I think it's a breaker. So, okay. So, this is the vector corresponding to the response variable, which is mortality. So Y is mortality. And then I can get in a number of rows, and as you can say, that's 60. There are 60 cities. And P, there are 5 columns, and that's the number of columns of X, and that includes the intercept. So there are 4 predictors plus the intercept. Now I can combine, I can C-bind, that means column bind. I'm going to combine X with Y into one matrix. And I said to list the first 5 rows, and so that's my data including the Y. And the Y is, of course, the mortality rate. I think it's mortality rate per 100,000. So at any rate, if you actually look at where we are, we briefly talked about the normal equations back in chapter 14 when we were talking about multiple regression. And I did it in terms of sum of squares and cross products. But more generally, the normal equations look like this. If you take the derivative with respect to each of the betas and set them equal to 0, you get x prime x, where the x is the matrix I defined here. Beta equals x prime y. Now you know the x's and y's. What you don't know is beta. Those are the regression coefficients. And that also includes the first beta. That beta is a vector. It is a vector of length 5. In other words, if we look at x prime x, remember, x is 60 by 5, right? And so the transpose of x is what? 5 by 60. So if I multiply a 5 by 60 times a 60 by 5, what's the resulting matrix? It's 5 by 5. So it's a 5 by 5 matrix. And beta has 5 parameters. Beta naught for the intercept, beta 1, which corresponds to the coefficient for rainfall, beta 2 for education, beta 3 for non-white, and beta 4 for SO2. X prime y, again, that's a 5 by 60 times y, which is a 60 by 1. And so x prime y is going to be a 5 by 1. So what you have is 5 equations and 5 unknowns. So you have a 5 by 5 matrix times beta, which is 5 by 1, equals a 5 by 1. So you have to solve for beta. Now, if I take the transpose, if I take the inverse of x prime x and multiply it by that equation, I would get x transpose x inverse times x transpose x, beta, equals x transpose x inverse times x prime y. Perhaps I should have written that out. But I'm going to multiply both sides of this equation by x prime x, or x transpose x inverse. Now if I multiply x transpose x inverse times x transpose x, what do I get? Well, on the left-hand side, I get the identity matrix times beta. And on the right-hand side, in other words, just beta. On the right-hand side, I get x transpose x inverse times x transpose y. In other words, the solution for beta is x transpose x inverse x transpose y. Now, that isn't really the way R does it. R does it by what's called a QR decomposition of x. In other words, it simplifies x into a matrix Q, which is orthonormal, meaning Q prime Q is the identity matrix, and times the QR decomposition, where R is a triangular matrix. It turns out that if you substitute QR into that equation for x, you can actually solve the system of equations quite easily, much more easily. And so R uses this QR decomposition, and I'll talk about that briefly. That's the one topic in terms of matrix decompositions that's fairly relevant to this course. But let's see how we do this in R. The transpose of x, remember, matrix multiply is percent asterisk percent. So the transpose of x, percent asterisk percent x, I call that xtx. That's just what I called it, but what that means is x transpose x. So this is the x transpose x, the 5. This is the left-hand side. And then I'm going to get, so let's go back here and take a look. So I'm going to compute this left-hand side, x transpose x, and there it is. And now I'm going to get the inverse. Now to get the inverse, we can simply say solve of x transpose x, and I'm going to get the inverse rounded off to 7 decimals. So if I multiply, that's the inverse. Now, if you multiply the inverse, I call that xtxi, I for inverse. X transpose X inverse is this second matrix here. So if I actually would multiply this matrix times that, I would get the identity matrix, or at least within rounding error. So how do I get B, the regression coefficients? Well, that's X transpose X inverse X transpose Y, so that's what I've done. xtxi, matrix multiply the transpose of X, matrix multiply Y. You see what I've done there? And that's B. These are my regression coefficients. So I can run that. Those are my regression coefficients for the intercept is 998.46. Coefficient, it's a positive relationship with rainfall. In other words, the more rainfall, then the higher the mortality. On the other hand, the mortality goes down with education. And it goes up with non-white percentage, and it goes up with SO2 levels. But are they significant? So those just tell us which directions they go. We don't know how collinear these are. We don't know whether or not, there's collinearity between those. Now, if we wanted to, we could obviously look at that, but that wasn't what I was trying to do here. Okay, so we have what B is. Let's get the predicted values. So Y hats are the predicted values. There are actually going to be 60 of those. So these are the predicted values. And here are the residuals. And I'm going to do a 5-number summary, which gives other residuals, which gives, what it does is give the min and the max. The min is the minimum residual is a minus 94.96. Max is 92. And then next you have the quartiles, and then you have the median in the middle. Now they should be somewhat distributed about 0, of course. The mean actually will be 0, but that's the median, not the mean. If I plot, I'm going to plot a reference line at h equals 0. Let's take a look at the plot of the residuals. So that's the plot of the residuals. So it looks reasonably well distributed, about 0. So these are the residuals from the model. Now sigma, if I want to estimate this variability, I can look at the residual squared, and in other words, I can sum what I'm doing. If you look at the sum of the residual squared divided by n minus p, where p is 5, that's the number of predictors included in the intercept. And I'm going to take the square root of that. So that's the standard error about the regression line. That's what I called in the book S sub y dot x. It's the square root of it, not S squared sub y dot x, but S sub y dot x. And so if I get sigma hat, that's the variability about the regression line. I can compute R squared. R squared, again, this is a bit of a review. It's 1 minus the sum of squares of residual over the sum of squares about the mean. And so I've just written that equation. And if I run this, my R squared is about 0.67 or 0.66. So we have a reasonably good fit, but you can see that we have some variation. Now in the book, how do I get the standard errors of the betas? The way you get the standard errors of beta is to multiply the sigma hat I got above, the S sub y dot x, as it's used in the book, times the square root of the diagonal of X transpose X inverse. Those were the P sub ii's in the book. So if I take the the inverse matrix, take the diagonal elements, and take the square root of that, those are the standard errors. Now, those are matrices. So let's take a look at the standard errors. And I could print those out. So B underscore SC, these are the standard errors for each of these terms. Now, in order to get the t-test, if you do your summary, when you're doing a regression, if you use summary of the model object, it will give you individual 1 degree of freedom for each term in the model. It will give you the estimate, the standard errors, and the t-value and the p-value. And we'll see that in a second. So I can compute the t. I can compute the t as the ratio of the b to this. Now, both b and the standard errors, those are both vectors, so it's doing element-wise division. It's doing element-wise division. So when I say b divided, it's a vector divided by vector, the same length, and so it's dividing each corresponding element. So those will give me my 5 t-values. So if you wanted to print it out, you could. Those are my 5 t-values. And likewise, the p-values, if it's a two-tailed test, I can look at the absolute value of the t, and then I could take 1 minus that and then double it. And so what I'm going to do, I'm going to c-bind b, the standard error, t, and the p-value. This is much like the type of result you're going to get for the book. And those are the coefficients, and then I'm going to name these coefficients. I'm going to name the columns, of coefficients. And then let's look at them. Now this is going to look very much like the results you would get by using summary. So I have my estimates, my standard errors, the t-values, and the p-values. And you can see that all of the regression coefficients are significant. So it appears that all 4 of those variables contribute. Now, so what we did was sort of replicate what you might do with LM. And so let's see what happens. I actually did LM, and then I automatically did a summary. So I did it all in one step. So I'm going to get the summary of Airpole, and then let's print it out. So I don't know if I can see all these on both sides. So you see, there's going to be effectively the same answers, although there could be some rounding error differences. And there appears to be, for example, in the p-value for the intercept. But you can see that the answers are effectively the same, except for perhaps some rounding errors. So if I look at the corresponding columns, I get the same results. Obviously, it's easy to do it the way I just did it. But my point of doing this exercise is to sort of show you what's going on behind the scenes. Although this isn't exactly, as I mentioned, this is not exactly the way R computes things. Taking inverses can be unstable, particularly if you have near collinearities in your x's. By that I mean, so what do I mean? If I take the x matrix, suppose I just took the x matrix, remove the intercept. Suppose I just took those 4 columns. And I might do things like get the determinant. Because if the determinant is 0, then that would imply there's a singularity. Well, I'm not worried so much about a singularity. What I'm worried about is if there's a near collinearity. So let me sort of try to illustrate this visually. If this table is x1, these 2 edges are x1 and x2. and my data is sort of, and this is y coming up straight vertically. And my data is sort of like this. And suppose there's very little variation. If I project my data down to the x1, x2 plane, suppose it's very tight. That is, the correlation between x1 and x2 are very, very high. So if you think of it as an ellipse, it's a very long ellipse that's narrow. So if you think about fitting a plane, and if the support under that plane, if the data is very concentrated, then the plane can wobble. If you just change one x a little bit, it can tilt the whole plane. You see what I'm saying? And so, you know, think about the data being highly concentrated in the, if I project it down to x1, x2, it's highly concentrated along a straight line. Not exactly a straight line, but highly concentrated. So if I fit a plane up in this three-dimensional space, if the plane is sitting, that I'm fitting, is sitting sort of through that data, if the support of the data, if it's not very wide, just slight changes in the x's can tilt the plane one way or the other. That greatly changes the coefficients, and we have an instability. That will occur if x1 and x2 are nearly collinear. So
you have enough working machines?
We do. It's just they don't have working machines.
First two rows are out.
Yeah.
Okay. Well, I called them. I don't know how long it's going to take them to look to get here, but
yeah, since it's all these rows and not the.
that one's on.
That one's on, yeah, but that may be on a different
I
one.
mean, this one right there.
Oh, did that come on now?
It's on.
Okay. Can you get on there over here? Or maybe it's just this side.
Oh, maybe it's this side. Okay. We thought maybe we'd look if it's, see if it's just a breaker, we can plug that in the box.
Okay.
Because who knows how long it'll take them to get.
Yeah. If you can find it. So it appears to be this.
Machines, right? You got plenty of free machines.
Yeah, I won't my next class though. It's full.
What time's that?
At 1.
Okay.
So
All right. You know where the breakers?
I don't.
We'll look around.
I don't know if it's a.
Start flipping.
Usually the janitors don't come in until 5 or something, 4 or 5.
Okay. Let's see what we can do.
Okay, thanks, Steve. So at any rate, you can see that we reproduce the results. I invented all that in one statement, LM, and then I did summary of LM. But typically you do LM and then you do summary on the object. But I just did it in one statement to show you that you get the same results. Now, if I go back and look, so these are the results right here. Now, I just wanted to mention that the way R will do this is it will decompose X into the product of QR, where Q is orthogonal, meaning Q is orthogonal, meaning Q prime Q is equal to I, and R is upper triangular, which means that you have, in the upper right-hand part, you have values, but in the lower left, you have zeros. Well, those are values, but they're zero values. And I had defined upper triangular. Now, it turns out that if you think about a system of equations, and if I had R times beta is equal to something on the right-hand side, it's an upper triangular matrix. It's very, very easy to find the solutions. Because if I start at the bottom, I simply have one number x times, or is some R value in the R matrix. Simple. One number times the coefficient is equal to a number. So I can simply divide the right-hand side by the corresponding number in the left-hand side and find the last coefficient. Once you find the last coefficient, then you can find the next to the last. And so you work upwards. It's actually very easy to do even by hand. It's called back substitution. So if you actually, back in high school sometime, if you solved a system of linear equations, what you did was to reduce it to a right triangular matrix, and then you back substituted to find the solution. That's how you did it by hand. That's how it does it in the book. Now the QI decomposition, by doing that decomposition, which is numerically very stable, And there are a number of methods for doing that. The Graham-Smith is the most commonly used. It may be the one you actually did in high school, although you didn't know it was the Graham-Smith, perhaps. And then there's others like the Householder transformation. There are others that perhaps are better. Although it seems like it would be fairly trivial, one of the things you have to deal with if you're solving a system of linear equations, what happens if I do have a singularity? What do I do then? Well, your algorithm would have to take that into account, that you could have a singularity. So R is very good. It uses very high-level algorithms to solve these types of equations. So this, behind regression in linear models, is this QR decomposition. I did want to mention just a few things. You should read over this vector algebra stuff. The inner product of two vectors, the outer product of two vectors. The inner product is a single number. It's simply, if I take a vector x, transpose it times x, so if it's an n, if x is n by 1, x transpose is 1 by n. So if I have a 1 by n times an n by 1, it will be a 1 by 1. So I'm simply getting an inner product. And those inner products are the kind of things you get when you matrix multiply. When I multiply a given row times a corresponding column, I'm getting an inner product of the ith row with the jth column. And I do that for all possibilities to do matrix multiplication. The outer product is less common, but it's doing xy transpose. So it's an n by 1 times a 1 by n. So if I multiply an n by 1, x, times a 1 by n, what do I get? I get an n by n. And so in that case, I get x1 times y1, x2 times y2. Those are the elements of the matrix. It's important to understand the concept of linear combinations. If I have a1, a2 up through am that are vectors, and then I have these scalars, s1 through sm, and if I take a linear combination of those, so I'm scalar multiplying s1 times a1, so that multiplies every element of a1 by the scalar s1. And likewise s2, a2, and so forth. That gives me a new vector, a. Now, if you think about matrix multiplication, if I have two vectors, and say these two, and I add them, it's like a parallelogram. So I actually get the point out here. It's the corresponding point when I add them. That's this distance between the vertices of the parallelogram. And so I can think about it geometrically that way. Now, it turns out, suppose I let V be the set of all A that are linear combinations of A1 through AM. Then V is called a vector space that's spanned by those A's. Now, the reason that's important is because, when I said this table, here's x1 and x2, I can consider all possible linear combinations of x1 and x2. And they sort of, any two vectors can span it as long as they're not collinear. So if I look at the table and I say, well, what is the vector space spanned by, say, this front dimension of the table and this side dimension? It's the whole plane that's sort of fits through those two vectors. That's the surface of the table, but going on forever. And so if I have a y, which is a vector coming up in the third dimension, then the regression fit is simply the projection of y orthogonally down to that table, and that's y hat. And from y down to the table is y minus y hat. Those are the residuals. So the predicted values is projection, and the y minus y hat are the residuals. Now, if I have a vector, if I multiply it by a certain matrix, it's called a projection matrix, or project it down. And I mentioned to you before, those projection matrices are symmetric idempotent matrices. And that's why they come into play. In the analysis of variance, what happens is that you actually have these sequence of projections that break up the model into pieces, and you get sums of squares for each of the terms of those models. And those sums of squares are actually these quadratic forms that are either typically positive definite. And so that's why all those things come in. But again, I'm just mentioning those for those of you that are interested. It's not something I'm going to ask on the exam, so don't worry about it. If I take a matrix A, it has columns A1 to AM. Let's say that's an n by m. then I can, I can talk about, okay, here's the, oh, I did skip one thing. Suppose, I could have linear combinations of the A's which give me 0. And if I can't find linear combinations, then we say the A's are linearly independent of one another. And in other words, if you can't find S1, S2, S3, Sm, of course, if they're all 0, that's going to occur. But if they're not all 0, and that occurs, then we'll say it is dependent. If you can't find S's, then we say they're linearly independent. Now, the columns of a matrix we can think of as being vectors, and then we can talk about things like what is the range of the matrix, meaning if I take the matrix A and I look at all the possible x's I could multiply, A times x, that gives me a y, then if I look at the range of A, it's all possible y's that I can get from any possible x I could multiply A on the right. By the way, multiplying on the right and left are not the same thing. XA is not the same as A times x. In fact, it may not even be defined because the number of columns of A must be equal to the number of elements of x if x is a vector. And that may not be the case if I multiply it the other way, unless A is a square matrix. So we have the range of A as a set of all y such that you can find an x such that ax equals y. And the nullity is a set of all x such that ax equals 0. And the rank of A is equal to the dimension. So the rank is an extremely important concept. And statistically speaking, it refers to the possibility of having collinearity. So I've been talking about collinearity off and on. And if I collected data and I had a midterm and I had a final, and then I had the sum of the midterm and the final, I have 3 vectors, right? And if they're in a matrix, if I have 25 students, it would be a 25 by 3 matrix, right? So for each student, I have a midterm, I have a final, and I have a midterm plus a final. So what is the rank of that matrix? It's 2. Because the third column is a sum of the other 2. Or put it another way, if I bring everything to the left-hand side, I can write it, that linear combination equals 0. So I have a collinearity. So that's an exact collinearity. And I know it's exact, and I wouldn't try to fit, I wouldn't be interested in fitting the midterm, the final, and the midterm plus the final, because the midterm plus the final is redundant information for linear type systems. So that's the type of thing statistically you usually know. What you don't know statistically is when you have a linear combination of the columns which is almost singular, which is almost a linear combination. And again, in the regression course, you look into more details about what do we mean by almost singular or almost collinear. One of the ways to look at it is if the determinant is almost 0. But again, you have to sort of look at, well, what does that mean? Almost 0. Well, we look at things, we often look at the smallest. Yeah, well, I actually didn't cover the idea of, the singular value decomposition. And that's perhaps the most important decomposition in statistics. This says you take a matrix X and it equals U, D, V prime, where both U and V are orthonormal or orthogonal, and D is diagonal. So if you decompose, the elements of D are called the singular values. And the singular values, small singular values correspond to collinearities. And typically, we may look at the smallest singular value versus the biggest singular value ratio. And if that ratio is too small, we know we have a problem. Another way we know we have a problem is if the determinant's too close to 0. But then the question arises, well, what do you mean too close to 0? And so that becomes problematic. To what extent is that scale dependent, for example? So these are issues that you'll cover if you take the regression course. You would cover in much more detail there. When we do diagnostics in regression, there are two types of diagnostics. We've done some regression diagnostics in this course. But when you do diagnostics in regression, you have what are called row diagnostics and column diagnostics of X, the predictor matrix. So the row diagnostics would say, do I have an influential observation? When I said that this plane may be unbalanced, I take one row and move it a little bit, and it causes the whole plane to tilt. That's an influential observation. It's a very precise way we define that. Those are called row operations. On the other hand, if I have collinearities, those are relating to the columns of the variables. And so those are relating to, well, do I have a problem because I have very high correlations? Not necessarily correlations of just the variables you measure, but of linear combinations of these variables. So those, again, are a little bit more advanced than what we're covering in this course. But the matrix algebra here will give you the background you need to go further in regression. Now, linear models, if you're looking at analysis of variance models, you don't tend to get into this problem, because there you have these dummy variables which are zeros and ones, and if we have balance, we have things are orthogonal or orthonormal, and so we don't get into these issues of collinearity unless the design is extremely unbalanced, meaning the observations in each cell are very unequal. So at any rate, this sort of finishes it off. So what I'd like to do now is to go back and look at, I'd like to quickly look at the exams. If we look at, in other words, what can you expect for this exam? So let me go in and look. And I'll try to give you some indication of what I'm thinking. The midterm covered, just in the very first part of Chapter 12, there was one problem on nested designs. The rest of it were on Chapters 9, 10, and 11 primarily. There may have been something, I don't remember if I did something on Chapter 8, but the main gist of that exam were 9, 10, and these three chapters. I did, as I mentioned, I had one question relating to the nested design in Chapter 12. So what did you cover in Chapter 12? Well, you covered, in the first part, you covered designs, like, besides nested, you covered the block design and Latin square design, right? Then what? Then you got into the two-way and three-way analysis of variance. And previously, back in Chapter 11, we had gotten into what is the concept of a random effect. But there was only one term in the model, so we had a random effect. Chapter 12, when we have more than one term, we have like an A and a B, two factors, then A could be fixed and then B random or vice versa. So we have what are called mixed models. So when you get mixed models, you get into the question of what are your error terms. And because we have to compute the expected mean squares, do you remember the rules for doing that? Well, you should review them. So we got into things like the expected mean square and how do we determine the test based upon that. And the expected mean squares were simple rules that would say, okay, if you have a term, then which other terms higher up are in the model? So typically a term like B, if it's a random effect, it would go in the model, but if it's a fixed effect, it wouldn't, at least using this, what's called the standard model. Well, let me just sort of, before I get too much further on this, let me just say that my intent is to have roughly 2/3 of the exam on chapters 12, 13, and 14. So 65 to 70% of the exam will be on chapters 12, 13, and 14. I probably will not give another question on the nested design since we've done that and there are plenty of other questions to ask. So that means about 1/3 of the exam will be on 9, 10, and 11. Mainly, I may give one on 9, but I'm most interested in 10 and 11. And in 10, that's just a one-way analysis of variance, right? But what did we, in fact, what was something that was really kind of unique that we did there? Well, we started looking at things like multiple comparisons. Tukey's test, Chaffee's test, and of course Fisher's, OSD. But we also looked at orthogonal contrast, and at the end, I added some material. We talked about the Bonferroni, which was a way of controlling the global alpha rate. But I also brought in the concept of family-wise error rates and false discovery rates. And I showed you how to do this in R. So again, the thing that I would be most interested in getting into in terms of exam is, do you know what is the difference between Tukey's HSD and Fisher's OSD, things like that. I believe I had a question on orthogonal contrast, but then I would also be interested in getting into something like the Bonferroni, the family-wise error rate, and the false discovery rate. I had some notes on that. At least know the central ideas about what do we mean by them, and how would you do them in R. So in chapter 10, I would be focused more on that than just the simple analysis of variance. In other words, if you reject and conclude there's a difference, then you do these follow-up procedures. Now, the main thing that was introduced in chapter 11 that wasn't in 10 is the idea of a random effect. And there you're not so much interested in contrast, you're interested in like the interclass correlation. You're estimating variance components. So your focus is a little bit different, when you get into random effects. Now, before I come back to 12, let me just mention, so what type of questions can you expect, and how much longer will the exam be? I think you had to work 8 out of 9. So the exam will be a bit longer, but not double. Probably not even 50%. It will probably be something like 10 out of 11, and again, I'll give you a sort of a question you can delete. It'll be something like 10 out of 11. Depends on how many parts are. It could be 11 out of 12, or the most I would do would be 12 out of 13. But again, that depends upon how many subparts of the question there are. The more subparts there are, it'd be more like 10. If I had fewer subparts, it might be as high as 12. 12 would be 50% greater. That would be the most I would do. So this is a 2-hour exam versus a 75-minute exam. But it probably won't be 12. It'll probably be 10 or 11 out of one more. 10 out of 11 or something like that. The types of questions will be similar. I would expect you to be able to write down, in other words, what is the model formula in an LM? So there's some R code I would expect you to be able to write down for the common cases of what you did. Like how do you write, if I gave you some data, and what is the LM fund? How would you analyze it using LM? So there are some basic things that you can use. Oh, before I forget to tell you, you can have 2 sheets of notes, front and back. And one could be the one you use for midterm, or you can do 2 new ones. That's up to you. So 2 sheets of notes for the final. Did anyone check me as the final this Thursday at 11? So it'll be in here this Thursday at 11 a.m. until 1. Okay, just to get a few things out of the way here. You can bring a calculator, but there won't be much computing. But you can't bring a smartphone or a tablet. So again, if I go back and take a look at chapter 11, and I look at the HTML file, see the focus there again was on the random effects model. So you should understand the model, and you should understand how to estimate the variance components. The follow-up procedure is a little bit different here. And the difference between the fixed effects and the random effects model, the expected mean squares for both cases, and then of course in all cases you should be able to look and understand how you assess the assumptions of the model. Okay. So again, the mean versus the variance plot is often a fairly important one to indicate that does the variance change. Under analysis of variance model, the variance should not depend on the mean. But sometimes it does, and so you may have to take corrective action if that is the case. Okay. You may have to use a transformation in that point, and there's an initial discussion of transformations here. Okay. So again, those are the kind of things. If you go back and look, particularly at the HTML notes for each of these sections or chapters, they're the kind of things that you should look at. So going back to chapter 12 now. So in sections 2 and 3, we looked at block designs. And the block design is an example where you typically have a block effect, which is typically random, and then a treatment effect, which is typically fixed. And so we have a mixed model. But in a block design, we assume the interaction. We typically only have one observation for each block, for each treatment, and therefore we don't have the degrees of freedom to fit the interaction term. So we typically don't have a block by treatment interaction. We assume that doesn't exist. Now again, that's assumption. If that assumption is violated, then you have some difficulty with that block model. The Latin square, you remove two sources of variability. That's a less important model than the block design. The problem is that you have a block where you have rows and columns and treatments, and they all have to be equal. So if you have A rows, you have to have A columns and A treatments. This came up in agriculture primarily, and there are cases where you can design an experiment in the layout of the field. You have drainage and so forth, and you want to control those two sources, but you have that constraint that the number of treatments must equal the number of rows and columns, and that doesn't happen that often, that you can force your treatment design into that form to get a proper experimental design. But as I said, going into the next two sections, the two-way and the three-way analysis of variance, that's where you really get into the idea of fixed effects models where everything is fixed, random effects models where everything could be random, but perhaps the most important type of model is the mixed model, where some of the terms are fixed and some of the terms are random. And when you do that, you're going to have to figure out what your error terms are. You're going to have to get the expected mean squares. So you should know the rules of computing the expected mean squares. It is quite possible you will have to do that. Now, section 6 and 7 got into what you call hierarchical or multi-level models. And 6 we call that a split plot. And the real thing is that in the whole plot, we have a block. This is the whole plot here. We have a block design. We have the block effect, the treatment effect, and then this error term is sort of like the block by treatment interaction. And then we have perhaps measurements over time in the subplots and the interaction of alpha, which is the main effect with this. And so that's our model. So understand that model and what the assumptions are here, how to compute the expected mean squares, how do we test things. We're often interested in this, the thing we're most interested in typically is the alpha-beta interaction. And that's this interaction plot which I had drawn down here. By the way, of course, the interaction plot for any of these 2 and 3 ways might be important, particularly if it's a fixed effects or fixed effects. And then so you can take a look. Again, you should review that. That's a very important topic. And then in in section 7, we have a variation of that, where we have repeated measures, and that model looks similar, except that in the whole plots, we have treatments and then we have subjects within treatments. Instead of having a blocking effect in the whole plot, we have experimental units within the treatment level. So it's more like a completely randomized design as far as the whole plot, and then we have repeated measures. Whereas the split plot we did earlier was like a block design in the whole plot, and then we could have repeated measures of some other subplot type effect. So the main difference is the whole plot. In this case, we have experimental units. Within the main effect. So again, if we work out the expected mean squares, we can determine how we would test. So the factor A, the main effect in the main is tested by this first error term, the B. And then factor C in the interaction is tested by the residual, or the remainder. So again, getting the expected mean squares and seeing what the error terms are extremely important. Now in both of these cases, we did look at some multiple comparisons and how we test those, and which error terms we use. So you should realize that. So again, you may want to take some notes on a lot of these things, just so you have them. So that was the main aspects of Chapter 12, and then in Chapter 13 we got into the analysis of covariance. So we got into the analysis of covariance, and that sort of combines regression with the analysis of variance. Now, in this Chapter 13, we only look at one covariate with one factor. Now, you can actually have more than one factor and more than one covariate. That's called multiple covariance. But again, what we covered was simply I did the wrong one, I think. What I meant to do was this. So this is our basic model. And I'm not going to worry too much. You know, these computing formulas here, don't worry about those so much. I want you to know the ideas about, you know, if you look at R, if you look at this example and you see how you test the various things, that's what I'm more interested in, that you know about. How do you test things? And so, again, if you review this, remember the covariance model looks something like this. In this case, we have 3 groups, and we have profit and a number of employees. This was at 3 different advertising media or something. And as the number of employees go up, the profit may depend upon the number of employees, but that may depend upon the advertising media. And so, again, we have 3 groups. I have different symbols there. And these lines are parallel. That's the case where we assume that the slope of the covariate does not depend on the group. So that's a simple model, but we have to test that assumption as to whether or not those slopes are the same, and that's in the next HTML document that I'll show you. So understand the covariance model and how you test it. Again, you're only going to be responsible for doing, you know, a single covariate with a single predictor. We're not going to go, but I want you to be aware that you extend this model. And using LM and R, it's straightforward to extend it to more than one covariate, more than one factor. But of course, you know, as I mentioned, we have certain assumptions. For example, we need homogeneity of variance. We actually need normality too. And again, from this model, we can get the residuals and assess either through a normal probability plot or a histogram or whatever. You can assess the normality assumption. The testing the equality of variances, that's a little bit trickier, but again, you can use various strategies for doing that, which we'll get to in a minute. We can test that the betas are all the same for all the groups, or that is, in fact, it could be that the common slope, that you don't need any covariates at all. So you typically start out testing, you know, are the slopes the same or not? And then if they are the same, you then test, well, do I need it at all? So if we look at it in terms of, the model, if I go on down here, let's see, where is this? This is a model where the slopes are not quite the same, but you can tell they're almost the same. So it's not likely I have an interaction here. So it means I can probably use a common slope model. Those lines are slightly different slopes, but barely. And that's why we don't need to use a different slope model. We can use a common slope model. But it also appears that common slope model is going to be very significant. That's a pretty steep fit. So look at this model, median plus employees plus. This interaction term is what you use to test. That term is what you use, the one with the colon. That, testing that effect, tests equality of slopes. So if I fit this model and I look at the test, in particular if I look at this F-test right here, the 0.22 with a p-value 0.81, that's testing that the betas are equal versus unequal. So here we accept the null, right? We say there's no evidence to reject, and that means the betas, we can assume and use the betas being common. Now once you do that, you might then drop down to test a model that looks like this, which doesn't have the interaction term. And there, if we test employees, then we're testing that beta equals 0. But notice when we test employees that it's highly significant. And so we do, obviously, we need to have the covariate in the model. It makes a big difference. Remember, if you look at those adjusted means were adjusted by quite a bit. For example, I don't have the other model, it's in the other slide, but these are the adjusted means along this line, where this is the overall mean for x. And the unadjusted means are way over here. So this mean gets adjusted from here up to here. This mean is already adjusted, and then this one gets adjusted from here all the way down to here. So the adjustments of the means are quite extensive in this particular example, what we call the adjusted means, adjusted to a common x, which is the overall mean. So those are the kind of things that you need to have, or know with the analysis of covariance, and how to check the assumptions. Okay. Then finally, in chapter 14 on regression, this first part is just doing a basic regression model. So remember we have, we're looking at predicted t-tests. Remember the type 1 and type 2 sums of squares, and you have the problem that in R, the order matters. And because R does type 1 sums of squares, and what you really want are type 2 sums of squares. And so you ought to understand that distinction in the regression model. And then we continued on in chapter 14. when we were looking at model fitting. And remember we said, well, R squared isn't by itself isn't very good, and the mean square isn't bad. We can sort of find a number of parameters that minimize the mean square. But better measures are the CP, which takes into account sort of both of these. It's somewhat like an adjusted R square. Mel is CP. And then we had the elimination and selection methods, backwards elimination, stepwise. And then we also had the, again, you should go through all of this, of course, criterion-based methods, which were the AIC and the BIC, which in R are quite easy to do. We talked about transformations. And that can transform the y or one of the x's, one or more of the x's, or both y's and x's. And if you look at this graph here, it gives you some indication. Where was it? This particular graph. You know, for the logarithmic, we typically transform the x. For the exponential, we typically transform the y. And for the power, we may transform both x and y. So you might take a look at that. We also had an example of polynomial regression, where you're finding the maximum. And then the final thing we had covered was logistic regression. I may not want a separate question on logistic regression, but I want you to kind of look at it. So I may have one question, one or two, which could be true or false. In other words, I may have part A, B, C, and D that are true or false, but I will ask you to explain your answer. We're not into a 50% guessing game. Okay. So that's the gist of what I would like you to have. Again, in some common cases, you may need to write R code, but that will be limited. Things like the LM function. Can you write model formulas? Being able to write model formulas is pretty essential. So you might have to do the LM function and a few common functions that I may want you to write. For the most part, I will either ask conceptual questions, or I will have R code and I'll ask you about the output from your R code. Or I may simply give you the R code and say, well, what is the output? So there'll be those types of questions where you get R code, and I may say, what's the output? Or I may give part of the output and say, interpret the output. In some cases, a few cases, I may have you write some common examples of R code. But there will also be conceptual questions. There'll be very little computational, but it's possible you may have to do a few divisions or a few things, so you might want to bring a calculator. Are there any questions? This, I think, is worth 200 points. Any questions?
When are you going to post the videos?
I'll try to do it tonight. For today, you mean? Which has what we just discussed. Yeah. I'll try to get it posted tonight because your exam is fairly early on Thursday. It's one of the first exams, so I'll try to get. How many? I've been trying to find out from Chen how many homeworks have been graded. How many have you gotten back? 5? Okay. So I think one of them is just sort of due in this time frame, and then tomorrow or something. And then, so hopefully she'll get the 6th one. There were 7. I'm going to give you 25 points. Is that 150 points? Is that what it is? So, what is it? Is it 150 or 200? Oh, it's 200. So, is she grading about 40? How many points is she? 25 points each. Yeah, so you'll sort of get a gift of 25 to sort of start things off, and then the other 175 come from the 7 assignments. Technically, I'm supposed to get this graded 2 days after the 2 days after I give the exam, which means sometimes this weekend. I doubt that they enforce that I get it in on Saturday, but they don't tend to enforce it anyway. It's just if you're late, then they have a problem. So probably by Monday, I should have everything graded. Any questions? I'll send out an email to both you and to the distance-based group, which, again, just to remind you of all the guidelines. But this gives us fairly, you know, as I said, about 65–70% of the exam is going to be on 12, 13, and 14. But there'll be certain areas, particularly in 10 and 11, that I mean, if you don't know that, you're going to have a tough time in chapter 12.
We don't need to worry about the computational formula for all the chapters.
Yeah, I'm not emphasizing those computational formulas that are in the book. They get harder and harder, and less feasible to actually do by hand, except for simple examples. So I'm not worried about computational formulas. Some of them are a bit intuitive. Like in some of the simple analysis of variance, it's kind of intuitive, but that's sort of not the focus I want to look at. Some of them are not intuitive. The computing formulas typically are not intuitive, although the actually way you construct them are similar to the way you calculate degrees of freedom, and you do need to know how to construct the degrees of freedom for all of these models. I forgot to mention that. You do need to know how to compute the degrees of freedom. That's very important. I don't know. I haven't decided. You know, on the midterm, I gave a couple where I said, well, here's an analysis of variance table, and here's some missing pieces. It's possible I might do one of those. That's just showing the relationship between degrees of freedom, sums of squares, mean squares, and F's. Of course, the F could be depending on the expected mean squares. Let's do it again. Do we have power? Hello? Yeah. I don't know. Do we have power? We don't. I'm just finishing up here, so I'll get back to you. Did anyone check to see if those SEIs are online yet? Why not? On Mix. They should email you on Mix. You should be able to link to it. As I said, I had trouble doing it last night. I thought I did it this morning. Okay, well, hopefully I can fix it. So you should be getting an evaluation document that you can fill out. It starts today and ends on before the exam, at midnight on the 11th. Is the exam the 12th? Yeah. So the next couple of days, hopefully I can figure out why it's not showing up. I'll remind you. Okay. See you Thursday.